Hi, I'm David Davis from ActualTech Media. We're here at the headquarters of Skyport Systems. I'm proud to be joined by Mr. Rob Rodgers. He's the Chief Architect at Skyport. How you doing, Rob?
Hi, I'm good. Nice to meet you.
Yeah.
Good to see you.
So I understand you have an interesting topic you want to talk to us about today. This is totally unrehearsed, and so I'm really excited to hear about something called the Big Lie.
We're going to do this live. So what I want to do is take a little trip down memory lane. And by that I mean I want to go back to the 1940s. And there's a guy named T.J. Watson who ran IBM. And what he said was, famously, he said, I think there's a use case for maybe 5 computers worldwide. And so let's picture a world with like 5 computers worldwide. You probably have one in the, I can't draw the United States, kind of looks like a cow, so that's the United States.
Right.
Let's call this Europe. There's Africa, which should be over here, but whatever. Maybe somewhere in Asia on the back and so on. I can imagine like 5 really big computers worldwide servicing every need that humanity has from a computational standpoint. So T.J. Watson was wrong. So that didn't come to fruition. And then about, I want to say 23 or 24 years later, there was this guy named Ken Olsen, who was the founder of Digital Equipment Corp. And what Ken Olsen said was, he couldn't fathom, and it was just at the birth of, there was a company called IMSI, there was Heathkit building home computers, there were the Apple I, and he said, and it was like 1977, which is approximately a few years after I was born, he said, I cannot for the life of me imagine why anyone would want a computer in their home. And so I have one of these, and you have one of these, and this is vaguely equivalent to what used to be called a supercomputer, was a Cray XMP, and this is about as much computation as an XMP had. So not only did we end up with computers in our homes, but we wear them on our wrists, we walk around with them, we carry them everywhere we go, they're enmeshed in us. And like the visions that we have of the future are, we'll wear glasses for augmented reality, where we end up having computers constantly integrated. I will look at you and I'll get like your dossier, or if I'm less cynical, I'll get like your interests, and I'll look around the world and I'll see people with augmented things. And so we're all heading towards like the meshing of computers with everything. And so these guys were completely wrong. But there's something kind of funny about what T.J. Watson said, which is kind of a myth that has been propagated in the last couple of years. And so if you take Watson's statement and replace computer with data center, then we start to see something that looks a little funny in that I have this data center on US West Coast, and I have a data center, say, US East, and I have Europe in Germany, and I have, say, Southern Europe, and then I have maybe a DC or a pair of DCs geographically separated in Africa, and I have DC Asia, and I have DC Japan, and so on. And so what I have is I've built out a data center in the cloud service provider sense is a giant computer. It is true that it presents as a virtual machine, but every process that runs on a computer is a virtual machine. And so the funny thing about this is that somehow approximately, let's see, it's 60, almost 80 years later, or 70 years and change later, we've adopted this idea that where we're going is that there will be some relatively small number of computers worldwide that we're all just going to use. And that flies in the face of the reality that we've lived for the last 60 years. It just doesn't make, it doesn't make sense. The reality of the future is not that there are going to be a few large data centers. Data centers scale really well. They are an amazing, basically modern data centers as pioneered by like Amazon and Google and so on. These guys have built these giant machines. It's almost like the computer equivalent of factories where aluminum comes in one side and fighter jets come out the other side. They've built these giant purpose-built machines to do computation. But the problem is that not all computation is location agnostic. And what we end up with is this sort of the vision of the future. So 4 years ago when we founded Skyport, when we were looking at raising our Series A, we ended up raising from the VC that incubated us, and they did a great job doing that. But we actually talked to other investors, and every investor we went to would say the following: dudes, why are you doing this on-premise cloud thing when 5 years from now, everybody knows everything will have gone to cloud? It's been 4 years and approximately 6 months, and aside from the fact that most of the customers we talk to have barely even gotten started moving to cloud, and not only has Gartner started to release reports where they're kind of suspecting that not everyone is going to move everything to cloud anyway, the proliferation of local compute has just taken off like crazy. First, there were companies that are doing sort of CDNs and POPs, where moving the compute and the data closer to the customer has been like a huge advantage from latency, from volume, from cost. From a real standpoint, people who think everything is going to cloud have kind of bought into a sort of big lie that benefits the CSPs. And it's not that the CSPs are doing something wrong by saying that, because they would like to gather as much as they can. But the reality is that if you look at the world and you look at how compute works, you end up with a situation that kind of looks like this. I have a whole bunch of data, and I need to run some functions over that data. So this is a perfect model of, like, this is what computation does when you have pools of data.
Right.
Another version of that is I have streams of data that are continuous, and I'm running some function over that stream of data. These two concepts are not location dependent. They're not location dependent, they're not independent. This one needs to be close to the data sources. I have a bunch of sources. They're flowing data into my system, and then I'm going to do something with it. I'm going to react to that data, and I'm going to perhaps produce more data out the other side, but perhaps I'm doing information reduction. This case is the case where I have a very large corpus, and I want to run some arbitrary function over the corpus, and I want to see what I can learn from that data. This is your machine learning case. This is your large user database case. This is your ad tech case. This is anything that involves large things, social graphs, anything like that. There's another version of this actually, which kind of looks a little bit like the opposite. I have some function that I want to run over a single stream of data that I want, as a result, this thing generates a number, it expands out the set of streams of data. So this is a case where I have a stream and I amplify it to multiple streams, and this is a case where I have multiple streams and I do information reduction and data reduction to get it down to a single stream that's more manageable, or which is more concentrated from a data standpoint. And again, none of these sort of structures have anything to do with location of the data, but all of them imply something about the location. And in particular, this one implies that the compute has to be brought to the data because the data is relatively immobile. This is a great use case for the cloud service providers.
Right.
So CSPs have mastered the art of storage at scale. They're fantastic at it. If you look at what Amazon initially did with regard to, say, Dynamo and the rest, and their elastic block store and so on, they've done an amazing job taking sort of cheap, garbagey kind of equipment, like masses of hard disks, and customize low-performance hard disks or low MTBF hard disks, and turn them into a very powerful mass service. They're insanely good at that, and then they allow you to deploy compute near the data. So in particular, their pricing models kind of drag compute to the data because you can't bring things out of the cloud as cheaply as you can put them in. One direction's free, the other direction is very overpriced and expensive. The other two are kind of interesting, right? In the case where I'm aggregating a bunch of streams together to get a data reduced but more valuable stream, I need to be as close, for this to be meaningful, financially or economically meaningful, I need to be as close to these streams as possible. I need to be at sort of a natural junction point. And so that starts to get a little closer to something that does imply location, like locationality or sort of geographic or network locations start to matter a whole lot, because these have to be cheap links. And they have to be very fast, especially if I have either a lot of sources or any of these sources is high volume. In the other direction, so that implies that this function is being dragged this way. And those sources are not just telemetry. They're things like video feeds, they're audio conferencing, they're things along those lines, often real time, but not always.
Augmented reality?
Augmented reality comes in this direction. Okay. VR comes in this direction. Real-time conferencing comes in this direction, although conferencing is also a good case for the next one. This could be autonomous vehicles that are generating each autonomous vehicle according to Mobileye. For example, the Mobileye CTO kind of said that on average, they generate about 100 kilobytes worth of data per kilometer driven when they're doing maximum collection, and more like around 10 kilobytes, which by the way was very surprisingly low, per kilometer driven when they're just doing ordinary collection. So if you look at that kind of number, it's like, well, 10 kilobytes is nothing. I send that over like an LTE link. Sure, but if I've got like 100,000 vehicles all gathering that telemetry, I want to do this somewhere as close as possible to the LTE termination point. So I want to perhaps be in a carrier, mobile carrier POP, where I can do my data reduction there before I bring it into my cloud service, or before I bring it into my data center or my locations. So this is your aggregate and reduce case.
So the data center and a cell tower.
So this is the data, not just a cell tower. I mean, most mobile networks actually, I worked in GGSNs for a while, so the mobile network is really complex, but the thing is, the closer you get to the tower, the worse your bandwidth gets from a networking standpoint.
Okay.
So the towers are aggregating a lot of bandwidth, that seems like a lot of bandwidth from a mobile standpoint, but when we're talking 100 gigabit services and so on, or multi-channel DWDM services, what you have is a bunch of regional backhaul networks where you bring it back to like your home network, your home agent kind of structure, and then you do a lot of processing on that, but that's still like inside the carrier networks, and then you bring it out onto the public internet, and then you bring it out into other services. Okay. So you'd like to do as much data reduction as you can. You'd like to do data reduction at the sources, but that means your sources are really smart, which means you have to send updates, software updates, and so on to those sources, which becomes really complex. Especially since you might want this source to generate a lot of data and this source to not generate a lot, and this one, like, I want 10% of these cars to do very high volume collection. No single car can do data reduction in that case because I need to do cross-car data reduction. So I need to aggregate it before I can filter it. I'm basically running F over a bunch of strings and producing a single string going up. In the other direction, I have a case where I want to do fan out. And fan out by definition is, I could do fan out. So let's imagine that I'm doing something like WebEx. And WebEx maintains a bunch of data centers worldwide, but inside a given data center, a call terminates at the data center, and then each call receives a copy of the audio stream. So they're multicasting, not using internet multicast, but using multicasting in the sort of the packet reproduction sense. They have multiple flows coming out of their data centers to feed the individual callers. Everybody has a copy of the audio stream. Now, if I'm a company and I'm trying to host a company meeting, and I have 10,000 employees, and 2/3 of those are at one location, one campus location, and there's 3 or 4 other campuses. That big campus location cannot possibly, if I want everybody to attend, I don't want to have thousands of redundant streams coming in. So what I want is because this pipe is limited, what I want is to get inside my network where the pipe is essentially free and unlimited. And I would like to do my replication inside. And so that means that by definition, this function that I'm moving close somewhere, it has to be as close to where it makes sense to do the fan out as possible.
Like a CDN?
Like a CDN, or even closer, I could have an on-premises, like for example, if I have a CPE router, I could have the CPE router do multicast replication.
Nice.
Or I could have a server inside the corporate environment that basically is providing this multicast replication. So Netflix's model kind of works like this, where they insert their movie thing inside POPs, and they do replication in a place where it's infinitely cheap. If you can be on a LAN environment, switching and packets are essentially free. So by definition, this case is very, from a network location, the topology of the network, this case is insanely close to the LAN switching environment. This essentially has to be on-prem. In this case, I have to be essentially somewhere in the mobile network, but I'm dragged there because I'm getting close to these virtual pools of data. The pools of data are streams, but I'm forced to go there. There's another case, which is very specific to Skyport, which is sometimes this sort of data aggregation thing is true, but it's kind of the mirror image of what's acceptable to put in cloud. So we have another case where you want to have this cloud-like structure of data that you maintain and functions that act on that data, but you want to keep them in, you want to be able to hug those servers. You want to go somewhere where the server is yours, and you can audit it. You have full control of the entire stack. You see everything there is to see. There's nothing denied you in cases where you own your data center. The issue there is complexity and cost. So this is like, essentially, when you listen to the CSPs, or you listen to like everyone knows, by the way, in general, when everyone knows something, what do we normally mean that to be? Normally that's the sign that the market has shifted into a way that is actually incorrect. So all of these use cases fail to work in the cloud model. At least cloud as the CSPs have defined it. Yeah. So what we think is, so to bring this back to Skyport, to talk about what we think about this, what we think is that Amazon has created a gaping vacuum. So Amazon has taught the buyers of compute, all of them, even the ones who are still running VMware back at their offices, even the ones who are investigating the Potemkin cloud that is VMware cloud on AWS. Amazon has taught, and Azure and GCE, they've taught people how to buy. They've taught them how to consume. And what they've kind of taught them is that you have this experience where you either have an API or you have a GUI. And they've kind of taught it that like all of the underlying stuff is all done for you. Yeah. No one has ever patched an Amazon instance of Zen, which is the hypervisor that Amazon uses. You never see it. You can't see it. It's taken care of for you. No one has ever written a network security policy on AWS that actually is policy of the AWS switching layer. What you can do is write software policy in the VPC layer, which is a logical construct that lives up here at your application layer. So you have your application layer and then you have your infra. And what Amazon has really taught people is that the infra should work this way. They've learned how that's going to be. And let's assume that the CSPs are very successful. Let's say that, I don't know, let's call it 80% moves to cloud and 20% stays on-prem for the reasons that I gave. Okay. Right? If 80% moves to cloud, then the dominant management model, the way people are going to want to consume and interact and manage, and the things that they're going to want to be responsible for, are going to look like this. And so this 20% is going to need to conform with how this works, because there's this cycle that's going to go on in terms of, oh, I moved this application to AWS, I moved it back. When it moves back, it's been transformed. You want to run it this way. And what VMware has failed at, in our view, and what's created a sort of gaping hole in the market, a vacuum that we hope to take advantage of, is we believe that you can't continue to have this model where it's like cobble it together yourself, buy this product and this product and this product, and kind of try and assemble it yourself. Right. Instead, you need something that kind of holistically works. The other big thing is that there's no local footprint. In AWS, there are thousands of servers that are used to run AWS. But you as an AWS customer have never seen them, and you will never see them. They might as well not exist as far as you're concerned. You spin up a VM, you spin up a VM. You never see that footprint. And here, that needs to be true. And so what we think is going to happen, and sort of the big lie of CSPs is that everything will go to AWS. But the big lie of remaining enterprise infrastructure is that everything will continue the way it has, because after all, it's been like this for 20 years. This dynamic is creating a new way of buying and using compute on the enterprise infra. And so that's what we want to solve. We want to bring compute, cloud-style compute, we're trying to bring cloud-style compute to enterprise on-prem. And so everything about us, we have no local footprint. We handle all of the patching for you. We handle all of the security management for you. If there's a CVE or a flaw, we immediately turn around and figure out, how do we address that CVE? How do we address that flaw? There's never a question of someone saying, well, I need to sign up for this patching service so they can track my hypervisors and see if they're ready. If you're running the software, you go to the UI, and if there's an update there, it means it's fixed. And if there's not an update there, it generally means there's nothing left to fix. And so you need to be able to consume it this way. Okay. This is our thesis.
I love it. So on-premises, AWS compatible cloud solution that allows you to move your workloads to and from the cloud, and it's managed in a cloud-like fashion where you don't have to worry about the management of the underlying infrastructure. Essentially, cloud-like experience locally with no local management footprint, and availability to deploy it anywhere in the world you want. So the one thing that we do really well in your description is, imagine I have a little branch office that needs some function over data, right? Some compute needs to be in some location, but I only really need, like Moore's Law has been amazing. I only really need one or maybe two servers. I can drop one or two servers. I don't have to have a vCenter instance. I don't have to be in OpenStack region. I don't have to have any local footprint at all. I put exactly what I need anywhere that I want to put it, and I manage it from the service.
So the hilarious thing, or the ironic thing about all of this, is that people look at Amazon and they say Amazon has commoditized compute. But if you, in my sort of naive understanding of what commoditization means, generally when something has been commoditized, it's gotten cheaper and the margin has gotten lower. But if you actually look at storage, bandwidth, and compute on AWS, none of them are cheaper.
Right.
What Amazon has done is convince the world that they're commoditizing compute so that everyone can be like, oh, I should go on Amazon because it's going to be cheaper.
Yeah.
But at the same time, what they are actually selling is they've done this amazing sleight of hand where they've taken compute, like have an x86 server, and they've swapped it for have compute as a service for this non-trivial premium that we've added to it. And that is, I admire them. That's an incredible thing to have gotten away with, but it has created an amazing opportunity and dynamic in the compute marketplace.
Fascinating. I mean, the big ad and the full page ad in the Wall Street Journal that the CIO reads that says, Amazon Web Services, just 2 cents,
Right, exactly. And then you actually do the math, and it's like, well, I'm trading CapEx for OpEx. I'm paying a lot more for bandwidth out. I'm paying a lot more for this. It's less visible. It's more opaque. It's something different. I mean, certainly if the guys down here had not made such a mess of IT and hadn't, we said this during Tech Field Day, if you look at like VMware, the security guide for VMware is like 600 pages.
Yes.
Why is that even 1 page? We don't have a security guide of 600 pages. We don't have a security guide at all because we take care of it for you.
I like that.
So.
Yeah. Very fascinating, very deep stuff. Thank you so much, Rob.
Yeah, it was great meeting you.
I look forward to learning more about Skyport Systems.
Thanks.